So we're going to talk about everything in the class. We're going to give it a unified perspective, and we're going to cover neural networks, PCA regression, feature engineering, and ensemble methods. This is like, you know, my favorite thing is how do we, so Poincaré, one of my favorite mathematicians, said a theory is, a collection of facts is no more a theory than a pile of rocks is a house. Meaning, how do we organize all these different algorithms into a consistent, coherent, overall theory? And so that's what we're going to talk about now. This is like fun grown-up topic time. Okay, so what we're going to start out with is before we get into this, just a really nice paper that I recommend reading. Titled is Do We Need Hundreds of Classifiers to Solve Real-World Problems? Terrific study here. They used 121 data sets with the whole UCI database. Their conclusion was, so 121 data sets, 179 classifiers from 17 different families. So several different implementations of random forest, several different linear regression, several different quadratic discriminant analysis, all these different families. Overall, they found that classifiers that are most likely to be the best were random forest algorithms. So it makes me happy we spend a little extra time on random forest, talking about how do you tune it. The big thing with random forest is it's pretty robust. You can throw a lot of different types of data at it. And if you ask me, like, why did that come up, it's probably because it's robust. I mean, and it's accurate, too. 3 out of the best 5 were different versions of random forest. And so they go through which were the best. They also go through which ones came from C, MATLAB, R, Python, whichever other language you're working with. So really good reference, you know, for lots of stuff. So it's the full version of what you're doing for your final project, right? There's probably all the data sets you have in your final project were done there, and you can go look up their accuracy if you want to compare. Not that I should tell you how to cheat your final project, but there you go. Okay, so when we talk about neural networks, we often draw diagrams like this, right? And we don't usually need them to talk about linear regression, because linear regression is pretty simple. So we have a bunch of input variables, x1, x2, x3. If we're talking predicting house price, x1 might be square footage, x2 might be, you know, acreage of the house, so on and so forth. And we want to predict something as our output. And so what we do is we pick a coefficient for each of our input variables. We multiply the value of the input variable by that coefficient, then we sum up. And so there's our formula, and that's our output. So the goal is to get these coefficients so that we minimize our error. And we're going to talk about the coefficients, but we're going to often write it just as a vector, that B transpose up top. Great advantage here is we can solve directly for the beta. Right? There's a formula you proved at week 2 or wherever it was. Right? It was great to prove it. It's the only time we can actually, one of the few times at least, we can solve exactly for what our coefficients are. Logistic regression starts with the same type of diagram. Similar type of things with our weights. We want to compute some weights, but we're not optimizing to the least accuracy with that sum. We're going to take the linear combination of those weights and we're going to put it into this sigmoid function, 1 over 1 plus e to the negative, and then beta transpose x. And what that gives us as an output is a probability. It's between 0 and 1. The bigger we have right here, beta transpose x, the closer this is to 1 over 1 plus 0. So that'll give us a higher probability over to this end. We train this not to get the minimum accuracy in something we can solve. It's an iterative training to minimize distance between each of these black dots on our curve and its associated weight dot, either above it or below it, depending on what class it's in. So we want to minimize error in that sense, in the sense of getting the best probability. And that plot up there comes from our code down in the corner. And so here we have an iterative search for the betas. Or for the beta, just one beta. When we expand the neural networks, when we look at a neural network, here's the diagram we typically draw. And so we have our input variables, our x's, and then we have a hidden layer, which we often call z's, and our output layer, which is just y1 if we're talking about regression for one variable or for predicting a probability for a class. You may have a couple of different y variables for outputs for probabilities for different classes. If we look at just one node in the hidden layer, what we're doing is we're taking each input variable, multiplying it by a weight, and then we're taking the sum of those, and that's what's going into that node. Then the thing that comes out of that node is the logistic regression formula, the sigmoid function, applied to the stuff going into it, and that's what gets transferred on up to y1. And so when we think about neural networks, if we just look at one node, it's exactly linear regression. So if you have a neural network with just one node, it's logistic regression. So neural network with just one node, that's logistic regression. With neural networks, the difference is we have a bunch of nodes. And here's my symbols, because I'm going to put those on a bunch of nodes, but I don't want to write, equations all over the place, so it'll get sloppy. So a little sum sign means I'm taking the inputs, multiplying by coefficients, and putting the sum into that. That little sigmoid function up there up top means I'm multiplying this to scale it before I send it on to the next stage. And so with a neural network, we're going to do this not just with one logistic regression, but a bunch of logistic regressions. So you can think about neural networks as an ensemble method of logistic regression models. And the thing here is we're going to train them to work as a system. And so we're not going to train this and then train that. We're going to train them separately. We're going to optimize them so that they all work together to give us the best accuracy as a system. And what we want to do is we pick a random set of weights to start with, and then we look at the accuracy at the end up at the y1, and we say, how can we tweak all our weights to get better accuracy? Then we'll adjust them a little bit, look at our error at the y1, and that'll tell us how we could tweak it again to get the best accuracy. So it's this iterative search, just like logistic regression, but we're doing a bunch at the same time. Two things we can minimize for, and we can iterate to minimize error. And that's kind of the first thing you would think of. And then you look at that, and often you'll get overtraining. And very often when we have these sort of iterated searches, we want to get the smallest error, but then there's a second penalty term that keeps us buffered from overtraining. Sometimes if we're doing regression, that penalty term might have to do with the number of elements in our models, like we do Bayesian model averaging. It's accuracy term that we want to get small, and the penalty term for having too many elements in our mixture models. And so here, our penalty term is some sum of the coefficients squared, and that's what our penalty term is. The reason that gives us this penalty is this. If you look at this red curve, that's e to the negative v. If I go e to the negative some large constant times v, it's a little hard to see here, but you get a very sharp transition. And so if you have large coefficients, you'll get sharp transitions in those sigmoid functions. And that puts a lot of decisive weight on one little piece of information. And so by putting that penalty on there, we avoid having one piece that's too decisive to the output. And when we go to train it, throughout this presentation, my black boxes there, or they're blue, I don't know, dark blue or black boxes, that describes how we train this thing. We're going to train it as an entire system. Hopefully, having our logistic regression broken up into a couple of different ones, hopefully they interact with each other, and they'll get different pieces of information that you wouldn't get if you just did one linear logistic regression, and you'll get better accuracy. That's the idea. We can think of that in a little more detail if we think of a neural network with a couple of different layers. And so this is a diagram of a neural network with 3 hidden layers. Right? So same thing we had before, but our first layer takes linear combinations of inputs, does something which hopefully the tuning gets that some inference or some piece of information there, and it passes it on to the next layer. Next layer is some linear combination of the previous outputs, and so on. And so here's the type of information we want a multi-hidden layer neural network to train for. And this is pictures from a convolutional neural network. So the inputs at the lowest level are just pixel intensities, brightness. Then the first layer is learning some low-level information. Here, just kind of bright and dark next to each other on different edges. So really the lowest level is kind of learning the smallest pieces of information that the higher levels are going to build stuff out of. So if you're doing a language processing thing, the bottom might be individual sounds as they're coming in. The first layer might be little bits of phonemes. The next layer might be combinations of phonemes and sounds. And you might want to build up words, and then up on upper layers, context of words and kind of full understanding of voice things. But here for vision's a little easier because we can look at it in a PowerPoint. The next step is little pieces of faces, or things that look like they might be little pieces of faces made out of the layer below it. So if you take combinations of things in this first layer, or layer 2 is the label is on it, then we add those together and we get things that are in the second hidden layer. And then those get passed and patched together to get full faces at the upper layer, or almost full faces. And so what gets passed in is here's a group of pixels at the bottom. Okay, the second layer will say, okay, I've got an edge here, an edge at this location, an edge here, and an edge there, passes it up to the next layer. And if those edges line up in the right spots, then they'll get a lot of influence going up in some of the segments. So you get high values at some of these Z's at the second hidden layer. And they'll say, hey, I've got a forehead here and a chin and a nose. And then when they're aligned properly to each other, the proper combination of those will get passed up to the next layer. So that's a convolutional neural network. Just kind of means we've taken groups and collected them together spatially for the next layer. We've done a convolution, a spatial convolution. One of the big advances with neural networks has been the idea of deep learning, which is training these things to get the type of information that you want. And so what often happens, we had a question last class, if I just throw a bunch of random weights, why are they going to train to the right thing? Why don't they just train towards just a repetition of the same logistic regression? Well, you know, they could, and if your random weights were all the same, they certainly would. Like if you weighted everything the same from the get-go, you would train towards the same thing. So we hope these random weights train to the right stuff. And so there's the neural network community, the advancements have been, how do we train better to get some good information out of our system instead of just giving it random weights and hoping it trains towards the right thing. And so deep learning is this idea of we want to help train some bits forward and some bits backwards to get this sort of deep understanding. It's also the idea of pre-training, doing some work before we do the training for the neural network. Okay, so back to the neural network. This is a single layer picture. If we look at the motivation, or we look at what's going on here, each Z is a weighted combination of the X's, right? So we take some of the X's, we apply weights, and that's what goes to the Z. And the idea is when we do regression on the outputs of the Z's, that'll give us better accuracy than just regression off the X's directly. But intriguing thing, this is really the same motivation we use for PCA. When we do PCA, we say you have your initial inputs. Each principal component is a linear combination of some of your principal inputs. And so we can draw PCA regression in the same diagram. So each, instead of having Z1 through Zm, each of those is our principal component, and it's just a linear combination of the input vectors. Right, so neural network, PCA. So when we think about one of the questions you'll read every once in a while or get on neural networks is, should we apply PCA before doing the neural network? Right, and so any thoughts from this on whether you should do PCA before doing your neural network? You wouldn't expect it to change much, right? I mean, maybe it would help something, but sort of in the framework, in the theory framework, it shouldn't. Like you wouldn't expect a lot. You wouldn't expect to need it. Yeah, exactly. Because the neural network, if it works properly, it'll properly weight all the inputs to build the next layer. So it would take care of the PCA within the neural network. Okay. The difference with PCA is what we do is we train this first layer on its own. I mean, we call it doing PCA on the predictor variables. And then we sometimes subset some of the predictor variables off if they don't get enough of the variance, and we train our principal components to capture as much of the variance as we can or as we want with as few principal components. And then after that, we train our linear regression on the inputs from the principal components. If we didn't do it in 2 stages, it would just collapse and be just linear regression. Another concept we talked about that's worth talking about in this framework is feature engineering. And so here is our Kaggle bike sharing example. Remember our inputs variables, we had Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday in the bottom there. And then we had some weather and month and temperature information. And one of the things we said is you could take that and put all that into a random forest and predict output. But you're going to get more accuracy if you group some of those before you make your random forest output. And so we could take our input variables and then we could make some grouped features. So 0, 1 on Monday, 0, 1 on Tuesday, 0, 1 on Wednesday, Thursday, Friday. Those are all weekdays. And so maybe instead of having all those separate, we just say, I just want a 0, 1 as a work day. And it would be the sum of the values from Monday through Friday. So this thing is just the sum of the values for the Monday through Friday. And then for Saturday and Sunday, those are weekends. So for other day, meaning like non-work day, we might take Saturday and Sunday and sum their values and get into the other day category. And then maybe we want to take some other date information into that, whether it's summer or holiday or something else to put into those days. And then the weather terms, maybe those features, maybe we just want to, in this picture, pass them on to the next level. Maybe we don't want to do much engineering on the weather terms, or maybe we want to engineer them a little bit and change them a little bit. And then working from the top down, we notice that there's this end class that we want to predict. That's the number of users each day. But we really thought that there's these two separate classes that feed into the number of users, number of casual users and number of registered users. And we looked at that by looking at that, well, they gave us category data, so we knew that was coming in. We could figure that's useful to look at. But if we didn't know that, we could do some sort of clustering, like run k-means on all your predictor variables. And you'd probably, if things worked well, if you told it, give me two classes, if it worked well, you'd get two different types of behavior. One behavior that would be more the casual user, and one behavior that would be more the registered user, right? Because the registered users tended to have different values depending on the combinations of the input variables. So if k-means works well, you might do clustering and find these two different groups, and you might say, okay, I need to structure and get two different groups. Or if you have some knowledge about the domain that you're working in, you can figure, okay, I need to group things in a certain way. And so off of this, we built two random forests, and they input into each of those two categories and then got passed on to the next level. So in a sense, we built this sort of multi-layered classification routine. We built it using some of our knowledge for just how people buy bikes and how weather would affect bike riding and how these different types of users would use things. So when we think neural networks, one of the reasons they get really accurate is they can infer this type of information. But you can also do some engineering or pre-training, or you could call it a different names, before you put your stuff into your data mining algorithm. Question? Yeah? Was there questions? No? Okay. So when you think of neural networks, it's trying to learn some of this stuff. But really, you can put some of this stuff in on your own. And what I often find helpful if I'm building a sort of a big structured routine for somebody, we have time to look at it, I'll try to train as much of it as I can, and then parts I can't train and I don't understand what's going on, I'll feed that in separately, and then I'll feed everything into a classifier and have the classifier sort it out. So parts of it you can train to what you'd expect, parts of it you'll leave separate and then feed it on, just like the picture here.
So you're saying a neural net can replace the random forest in the last slide?
So that's a really good question. Here we have these staged sums, and it's the first time we stuck a random forest in there. So
I can understand the picture engineering, how neural net can replace the engineering stuff, but how can it replace the random forest?
Yeah. So I'm not saying neural network would specifically replace the random forest. Certainly they're structured differently. Yeah. But this sort of multiple levels is structured similar to a neural network, where you have some understanding of some pieces at one level or one layer, and that passes on to the next layer. Yeah. Another algorithm we talked about was Adaboost. And so in Adaboost, we're going to take all of our predictor variables, and we take a single decision tree, a decision tree with a single node, which is my little diagram there. It's two inputs, one single threshold, and then one output. And then that's going to give us what our z-value is, and which will get passed on to the output. And what we do is we build a single decision tree and we train it. And then we build the next decision tree, right? Really simple decision tree, and we're going to train it and pass its level on. And its output gets multiplied by these alphas. They're going to scale the output, and then that little plus sign means we just add them together, right? And the alpha is trained when we train that node. And each node that we add, each simple decision tree or stump, it's going to be trained to pick up the error that was created by the previous ones. And so there's our Adaboost setup. All right, so you could think about it in this sort of these diagrams we usually draw for neural networks, but you think about it in the same sort of diagram, but instead of training one layer at a time or the whole thing, we train it sort of vertical columns, one after another. Remember, the goal here is each of these individual nodes is a weak classifier or a low accuracy thing, but we train them so one after another gives us high accuracy. The advantage is we get some of the low error rates or low tendency to overtrain from the single ones, not low error rates, but low tendency to overtrain. From the single ones, we combine them together, keep some of that robustness against overtraining, but increase our accuracy. And this is the one particular example of the Adaboost system, the Viola-Jones face detection. One of the ones where it said, hey, this is really, you put this together with some nice spatial grouping of pixels, and you can get a really fast, robust face detection.
So the Adaboost would, you say it reduce the tendency to overtrain. So that would increase the bias? Because decision tree is low bias. It's everything. You can train everything. But
yeah.
Adaboost only one stump. So
yeah, one stump at a time. Yeah.
So
they're each like very
high,
biased on the
very high
road.
bias.
We combine them, probably lose a little bit of that bias, but still keep a fair amount of the bias. Yep. Okay, random forest, we can think in a similar sort of way. I put the link to the random forest Microsoft document on the bottom, and I borrowed I like their little pictures of random decision trees, so I use those as my icons for decision trees. So each of our nodes is a separate decision tree, and when we go to train them, we train them all independently, and the random sampling of features and data that's going to go into them makes them each independent. And then, so we don't train them to work well, we train them to be separate from each other, and then we feed on their information to the next stage. Now, these sort of diagrams make you wonder, well, why don't I stick a logistic regression after those and take the best combination of my random forest outputs to the next layer? And so, I don't know why. Maybe somebody's done that, maybe not, I'm not sure. It's, maybe I should think about a second layer of random forest on top of that. No, I don't know. Bayesian model averaging is another thing we can think about. This helps us think about how each of these were trained and how that different training leverages to get the accuracy we're looking for. And so with Bayesian model averaging, we get a logistic regression. It's based on only some of the predictor variables, and then the output from that gets multiplied by the likelihood that this is the correct answer, and that gets passed on to our Y1. And then we train another logistic regression, and we look at how likely that is, or after we normalize the likelihoods, they become probabilities, and we multiply that and send it on. And then we train all of our different linear regression models. Depending on how accurate they are and how many variables they use, they get a likelihood. It gets multiplied by them before it gets passed on. And then typically, we want to get rid of some of them and say, these are the ones that didn't have as good of a likelihood. So if they're not in the proper confidence interval, they're not 1/20th as probable as the best algorithm to be the correct setup, then we'll get rid of them, so we just don't have lots of noise from a bunch of things that probably aren't correct anyway. Okay, how's that? Well, that was pretty quick. That was good. Okay, so I like to think about these sort of big structures. What's the thing doing as a system? What should it do? The neural networks are supposed to optimize as an entire system towards something. So one of the things you can do as a sort of practicing data mining engineer, whatever field you go into, computer scientist, you can build these things, but custom build them for whatever application you're working in.